Think about it. You've never, not once in your life, seen a shattered glass suddenly leap off the floor and perfectly reassemble itself in your hand, right? The universe just naturally flows toward chaos and disorder. We call this entropy. And for centuries, humanity has honestly believed that we could conquer this chaos, mapping the unknown using just our intuition. But eventually, we hit a wall. We reach the very edges of human comprehension, realms of infinite mathematical complexity that seem, well, completely beyond our grasp. Welcome to This Explainer. Today we're diving into a genuinely staggering breakthrough by OpenAI, one that challenges the absolute limits of human intuition when it's faced with unimaginable complexity.
Picture the vast, chaotic oceans of mathematics not as numbers on a page, but as a massive, swirling, unpredictable storm cloud. Billions of variables just colliding and interacting in this mesmerizing turbulence. For a long time, humanity has used the mind as a lone vessel, navigating these dark waters, a solitary explorer facing down the infinite. We just kind of assumed certain problems were way too dense, too chaotic to ever fully map. But what happens when a machine steps in and perfectly charts that storm? What happens when the chaotic actually becomes flawlessly mapped?
Let's start with Section 1, the limits of intuition. To really grasp the sheer magnitude of this shift, we got to look back at one of the 20th century's absolute greatest minds, Paul Erdős. He was a legendary, ridiculously prolific mathematician who famously tossed out incredibly difficult math problems just for fun. And one seemingly simple challenge was the unit distance conjecture, posed about 80 years ago. It goes like this. If you put an infinite number of dots, let's call them endpoints, on a flat, endless plane, what is the absolute maximum number of pairs that are exactly 1 unit of distance apart? Imagine taking a ruler of exactly 1 unit and just laying it between points on a massive sheet of paper. As the number of points grows to infinity, how many of those perfectly measured 1-unit connections can you possibly make? Now, what's really interesting is how our human brains initially try to solve this. We naturally think of a basic grid setup, kind of like graph paper. If you place points on a square grid, every point has 4 immediate neighbors, north, south, east, and west. This generates roughly 2 n pairs of unit distances. It's neat, it's orderly, but it's not very dense. Erdos wondered if some insane, deeply complex arrangement, like a chaotic storm of dots, could push this exponentially higher. Could it perhaps even approach n-squared pairs?
Which brings us to Section 2, counting mathematical cherries. As Erdos wrestled with this, he suspected that an overwhelmingly dense point set was actually impossible. But here's the catch. How do you prove a limit on infinity? Well, he did it by counting cherries. And this brilliantly illustrates the human approach to chaos. We find patterns. He defined a cherry as a specific configuration of 3 points, a central point connected to 2 others, both exactly 1 unit of distance away. By isolating this simple, elegant shape, Erdos created a mathematical boundary. He realized the total number of cherries in any given space couldn't exceed a certain limit, which tightly restricted how dense the points could ultimately be.
So here's how this builds. If you assume a single point has, say, 100 neighbors at a distance of 1, the number of cherries acting around that center is roughly 100 squared. By summing this up across all the vertices, effectively running on algebra autopilot using a mathematical rule called the Cauchy-Schwarz inequality, Erdős established an absolute upper bound. He definitively proved you simply cannot have more than n to the power of 1.5 edges. The chaos, it turned out, had a ceiling. But an upper bound is really just a theoretical maximum. Erdos strongly intuited, he felt it deep in his bones, that the real maximum was far, far lower than that. He suspected the true answer was much closer to simply n, capping his personal guess at an exponent of 1.001. He honestly believed the human mind, even at its absolute peak, could never conceive of a physical layout that would break this specific ceiling. It was the edge of the mathematical map, right where the dragons of chaos lived. But, always the explorer, Erdos decided to test his own limits. He realized he didn't have to strictly use a distance of 1. He could scale the problem up. So he started looking at larger grid distances to see if he could force a higher density of connections. And he discovered something totally fascinating. At a very precise distance of 65, the points on the grid suddenly exploded with an insanely large number of perfectly measured neighbors.
You might be wondering, why 65? Well, he ingeniously used 19th century number theory to find the answer. By taking prime numbers that leave a remainder of 1 when divided by 4, like 5 and 13, and multiplying them together, he could generate these optimal magic distances. This grid yielded connections growing slightly faster than n. Yet, even with this brilliant, masterful construction, he still failed to break his own n to the power of 1.001 ceiling. The human limit held firm.
Now we hit section 3, the AI breakthrough.
So here is where the story completely shifts, where the ancient human master hit an impenetrable wall. Gazing out into the vast unknown, a completely alien mind stepped in, a new kind of intellect, when entirely unbound by the biological limits of intuition and memory, took over the navigation. Recently, an OpenAI model tackled this exact 80-year-old conjecture. It didn't throw out the human work. It actually followed in Erdős's general footsteps, but then it achieved what generations of human mathematicians thought was physically and mathematically impossible. It completely shattered the conjecture, seeing straight through the turbulence of the storm.
The AI generated a highly complex asymptotic point set that definitively proved the number of edges can in fact grow faster than Erdős's absolute intuition limit. It pushed those boundaries right over the edge, hitting a confirmed exponent of 1.0101 per endpoint. Erdos was wrong. The ceiling was literally broken.
Let's move to section 4, memory versus human compute.
The truly fascinating question isn't just what the machine did, but how it did it. See, it didn't invent entirely new math out of thin air. Instead, it accomplished this by perfectly merging vast, historically distinct fields of mathematics in a way no single human brain has the sheer memory capacity to execute. Think of the human mind as an ancient navigator on a dark ocean. We guide our ships by the stars of intuition, spending years, like Andrew Wild spending 7 full years to solve Fermat's last theorem, just specializing in one domain. The AI, on the other hand, it's a futuristic dreadnought. It doesn't rely on stars. It uses flawless, instantly accessible radar. It has perfect memory across domains, allowing it to instantly fuse the visual spatial reasoning of discrete geometry with the heavy abstract machinery of algebraic number theory.
And the result of this incredible fusion is shockingly brief. Get this. The OpenAI paper detailing the solution is roughly 20 pages long, and the core mathematical proof compresses down to just 3 or 4 pages. The true difficulty was never the length of the calculation, it was the impossible breadth of knowledge required. Understanding algebraic number theory deeply enough, while simultaneously holding the intricacies of discrete geometry perfectly in focus, is something AI just achieves flawlessly through its immense encyclopedic memory.
What we are witnessing right now is basically the rapidly rising sea level of artificial intelligence capability. For a while, that water level was roughly at the height of an undergraduate thesis. Impressive but manageable. Now, that tide is surging. It's moving swiftly to conquer conjectures that have completely baffled humanity's absolute brightest minds for the better part of a century.
Which brings us to a profound, almost unsettling crossroad. If a massive, non-biological machine can perfectly navigate the most chaotic data, instantly fusing distinct domains to solve the unsolvable, what role actually remains for the human intellect? If the machine can flawlessly chart the stars, why do we even need the ancient navigator? This takes us to our final section, humanity's final stand.
The answer to that anxiety lies in something a machine, no matter how vast its memory or processing power, fundamentally does not possess: human intent, and that innate spark of curiosity. Sure, AI can calculate a flawless route through the storm and tell us exactly where the turbulence leads, but it absolutely lacks the intent to set sail in the first place. It doesn't have intrinsic curiosity. Humans alone stand on the shore and decide what is elegant, what is beautiful, and what is actually worth exploring. The AI answers the how perfectly, but humanity's enduring role is to point at the horizon and ask the profound why.
As this source material beautifully highlights through an old piece of mathematical wisdom, grinding out the proof is increasingly becoming a mechanical task, a job for the dreadnought machines. But defining the very concepts, deciding what is interesting, asking that first brilliant question, that remains our sacred domain. The best minds don't just solve, they define the parameters of reality itself.
And so, I'll leave you with this to ponder as we wrap up this explainer. As we inevitably hand over the compass of endless calculation and logic to artificial intelligence, as the machines map every storm, is humanity's final, unconquerable fortress simply our will, our intent, and our courage to ask the right question?